Hi there, welcome back. We just finished talking about friction, and friction is something that opposes motion. And now we're going to look at something very similar, something I like to call air friction, known as drag. So drag is essentially the air equivalent of friction, and we're going to take that apart a little bit today. Now, at the beginning of the year, when I first talked about free fall, I said all objects in free fall, regardless of their mass, accelerate at the same rate. And that's a very difficult thing to back up in real life. If I imagine dropping a bowling ball and a feather at the same time, then the bowling ball is obviously going to hit the ground a lot quicker. But we said that that only applies to objects that are in a vacuum. And now we're going to briefly just take a little bit of look at drag and see how that plays and helps us understand why that happens in real life. So drag, the drag force, it is a force, and exactly like friction, it's always opposite in direction to the velocity. So it's something that opposes motion. So if I'm traveling to the right, then drag is opposing that motion to the left. And an interesting thing is that it increases in magnitude as the speed increases. So it increases as the speed increases. And I'll address that a little bit more in just a second, but we also see that at relatively low speeds, which is a vast majority of what we do, the drag force is really small and it can be ignored, but as speed increases, so does the drag force, so it becomes more important. And the way, my quick little introduction into this, and we'll talk more about it, but if you think about air is a fluid. Water's a fluid too, but air is a fluid just as much as water is. It's just a different type of fluid. So if I imagine that in air, there are all these like dots, all these air, this is really not going the way I thought it would. There's all these air molecules. And as I travel, or I traverse the medium, if I want to walk, I have to push all these air molecules out of the way. And the faster that I walk, the more air molecules I encounter, so the more that I have to push them out of the way, okay? Just like if I'm swimming, the faster I swim, the more water I have to push aside. So these things kind of make sense, is that it's literally me pushing air out of the way. And we've all experienced it to some extent where if we're running into the wind versus running with the wind, right? There's all these air molecules, and they can help us or hurt us depending on what we're doing. So the drag force does have a very nice formula, but it's a little tricky. So the drag force, there's this half thing, there's this drag coefficient. And we had coefficient before when we talked about friction, but it's the drag coefficient exactly the same as the coefficient of friction, where it just kind of depends on what the object is. Then we have this factor of rho. And rho is density. From physical science or from other science classes, you know that rho is density, which is mass over volume. In chemistry, you might just have it called D for density, but it's actually rho. And so the thicker the fluid, the more drag you encounter. And that makes sense, right? Because if I'm running through air versus running through water, it's a lot easier when I have a lower dense fluid. A is the next thing. A is the cross-sectional area of the object. So if I think about like a parachute, a very, very wide parachute is going to experience more drag than a narrow parachute. And that makes sense because if I'm like in a military style parachute, I'm going to have a lower cross-sectional area so that I can go faster. So I encounter less drag. And then finally, the last little part is the velocity. So v is the velocity of the object. So I can see that as velocity increases, the drag force that I experience will also increase. So the faster and faster I go, the more drag I experience, because I'm pushing more and more molecules out of the way. Now, the problem with this is that we know that forces cause acceleration. So if I increase the velocity, I increase the drag force, and I increase the right? Increase the magnitude of the acceleration. In this case, this is going to be a negative force. It's going to take away from gravity or something. But if that gets me a new velocity, which gets me a new drag force, which gets me a new acceleration, which gets me a new velocity, which gets me a new drag. Okay, so the problem here is that by having the drag force, it makes things a little complicated. And the only thing that we can really do is take a look at a quick application of it, because the only way that we can correctly solve this mathematically is with differential equations. Unfortunately, Calc 3 is where you really get into differential equations, so we can't do a ton of it right now. But we can still talk about it, and we can take a little look at it without getting too deep into the math. So one of the easiest applications of drag is this concept of terminal speed. Terminal speed is just an application of Newton's first law. We have an object, in this case it's like a basketball, and it's flying through the air. Now there's a weight force that's pulling it down. It's accelerating down. When it first starts accelerating down, it's accelerating at free fall. And then there's a drag force that's opposing that motion. Now, as it gets faster and faster, it encompasses more and more drag. So the faster it falls, the further it's going to fall, and the drag force will increase. And it'll keep increasing, causing the acceleration, so that as the drag force increases, the acceleration will actually decrease, until eventually we reach what we call terminal speed. And at terminal speed, the drag force is equal and opposite to the weight. So that means then that our net force is equal to 0. There is no net force, there is no acceleration, and we're falling at some constant velocity with no acceleration. Acceleration equals 0. So the weight force is causing the object to fall, and then eventually it's falling fast enough that the drag force is causing an opposite force in the opposite direction, and we call that terminal speed. So if we're looking quantitatively at terminal speed, we can solve for velocity. We know that in this case that the drag equals the weight. The drag force is 1/2 times the drag coefficient times rho times the cross-sectional area times the velocity squared. And the weight force is mass times gravity. So if we solve for V, V is going to equal the square root of 2mg over c rho A. Okay, so not something you have to memorize, but a quick little application. One of the quick things we can do is generally we can approximate the drag coefficient as 1/2. So much like the coefficient of friction, this is a dimensionless unit, meaning that it has no unit. And for many things, the drag coefficient falls between 1/2 and 1. So for our calculations right now, we're just going to say it's 1/2. And that gets us one quick formula where the velocity is the square root of 4 times mass times gravity divided by rho, the density of the fluid, times the cross-sectional area. And honestly, that's about as deep as we can get with it right now because of the concept of differential equations and how it applies to this mathematically. So that's all we're going to take a look at. So we got a partner problem that we'll take a look at in class. But it says a 75-kilogram skydiver and his 20-gram pet mouse jump from a plane. Estimate their terminal speeds, assuming that they both fall in a prone position. So the only things that matter, according to my previous slide, are mass, gravity, rho, which is the density of the fluid, which I can actually, it's a constant for air, and their cross-sectional area. And the best way that we can approximate their cross-sectional area is by thinking about them as a square or a rectangle, however you want to think of it. And that's what's going to encompass or encounter all the drag force. So we'll take a look at that in class, and we'll solve that in class. And then we're going to finish off this chapter by taking a look at a couple different applications of Newton's laws and how they apply to very specific situations. Now that we're done getting a basic category of forces and how we can quantify those forces with equations.